Memory development is governed by the physical constraints of brain maturation. Our capacity to process and store information is dictated by this evolving architecture. In the first phase of life, the brain prioritizes raw adaptability over operational efficiency. It creates a massive surplus of neurons and synapses in a process called neural overproduction. This surplus is inefficient for long-term function. To optimize the network, the brain enters a fine-tuning phase. Regulated by brain-derived neurotrophic factors, the brain removes unneeded cells through apoptosis and eliminates unused synaptic connections through pruning. This graph maps the trade-off. Plasticity peaks early in development, providing the young brain with massive flexibility. Efficiency, however, is a late-blooming trait, rising only as the pruning process finishes in our mid-20s. This shift from high plasticity to high efficiency explains why we have early sensitive periods, why we forget our infancy, and the roots of adolescent behavior. Basic associative learning begins before birth, operating through early developing systems rather than the complex cortical structures that mature later. In studies by Peter Hepper and Sarah Shahidullah, fetuses exposed to repeated auditory tones showed a steady decrease in movement. The fetus was detecting the repetition and habituating to the familiar stimulus. This FMEG readout identifies the neurophysiological proof. The fetal brain maintains a steady baseline for repeated sounds, but produces a deviation spike, the mismatch negativity, the moment a novel sound is introduced. This early learning occurs at the height of neural overproduction, utilizing the surplus of available neural connections. This surplus defines sensitive periods, brief windows where heightened plasticity allows environmental input to rapidly and permanently wire cortical systems. David Hubel and Torsten Wiesel demonstrated the strict timing of these windows. When specific sensory input is missing during the critical period for vision, the visual cortex permanently wires itself around the remaining inputs, resulting in lifelong functional changes. The brain is born maximally plastic to tune itself to its specific environment, but this ability to rewire is time-limited. Despite these early learning capabilities, adults experience infantile amnesia, a near-total absence of episodic memories from the first 3 years of life. Behavioral tests confirm that infants do encode information. In the mobile conjugate reinforcement task, infants learn to kick to move a mobile, accurately remembering the action-outcome contingency for days or weeks. They also demonstrate episodic-like encoding through deferred imitation. After watching a sequence of actions with a toy, infants can replicate that sequence without prompts after a significant delay. Adults, however, cannot access these early experiences as autobiographical memories. This amnesia is tied to faculties that develop alongside the brain's physical maturation, including the language needed to structure narratives, and the self-concept required to anchor an experience. The biological driver is the developmental encoding hypothesis. The infant hippocampus is physically too immature to bind the contextual details of an event into a stable, long-term episodic trace. Researchers Sheena Jocelyn and Paul Frankland proposed the neurogenic hypothesis to explain how the development of the hippocampus itself triggers forgetting. In infancy, the hippocampus undergoes a high rate of postnatal neurogenesis. New neurons are constantly forming and integrating into the network, displacing the existing connections. As these new neurons integrate, they alter synaptic weightings and physically overwrite the architecture of established memory traces. In adulthood, the rate of neurogenesis slows significantly. This more static environment allows memory traces to stabilize and persist over time. The mechanism that allows the infant brain to be highly adaptable is the same physical process that destroys its earliest episodic memories. As neurogenesis slows and fine-tuning progresses, the brain relies on increasingly mature structures for complex learning. We can trace this maturation through eye blink conditioning, which tests the brain's ability to associate a tone with an incoming puff of air. In delay conditioning, the tone and the air puff occur simultaneously. This simple association is handled by the cerebellum, which matures very early. Because these cerebellar circuits are online early, infants succeed at delay conditioning tasks. Infants fail trace conditioning, where there is a temporal gap between the tone and the air puff. Bridging that gap requires the hippocampus, which is still undergoing significant development. Behavioral capacity is restricted by the developmental timeline of these specific anatomical structures. The final stage of cognitive maturation centers on the prefrontal cortex, or PFC. This region manages executive functions, working memory, and strategic retrieval. To reach maturity, the PFC undergoes 3 structural changes: pruning inefficient synapses, expanding dendritic branching, and insulating axons with myelin for faster communication. This process is prolonged. PFC myelination and pruning continue until approximately age 25. This creates a developmental mismatch in the corticolimbic circuit. The inner limbic system, governing emotion and reward, matures years before the prefrontal cortex can provide top-down inhibitory control. The limbic system operates at full capacity while the self-regulation mechanisms of the PFC are still being wired. Adolescent impulsivity and risk-taking are the functional products of this neuroanatomical mismatch. By young adulthood, the brain enters a stabilization phase. Plasticity has leveled out and cortical efficiency has reached its peak. This mature architecture supports the 2-component model of episodic memory. The first component is associative binding. With early neurogenesis finished, the hippocampus can reliably secure the raw details of an experience. The second component is strategic control. The fully pruned and myelinated PFC allows for organized retrieval and the use of complex memory strategies. Mature memory is a biological trade-off, sacrificing the adaptability of the infant brain for the stable executive control required for adult life.